In class, we've been talking about the idea of the electron, where we find the electron, how far away we find the electron from the nucleus, energy levels. And in that conversation, we talked about the idea of the electron moving around between different energy levels. Remember, we defined energy level as, these orbits around the nucleus, and we said the orbit that's closest to the nucleus, we're going to call n equals 1, and the next closest one is n equals 2, and the next closest one is n equals 3. And we said if an atom takes in some energy, it makes that electron move further away from the nucleus. In other words, it moves to a higher energy level from, for instance, n equals 1 to n equals 3. And so we would like to be able to calculate how much energy it takes to move that electron back and forth from n equals 1 to n equals 3. Actually, we're not moving it back and forth, we're moving it from n equals 1 to n equals 3, and we'd like to calculate how much energy that takes. In the next problem, which is going to be an extension of this, we are going to be looking at what is the wavelength of a photon that atom could be absorbing to make that electron move. And remember, we're looking at an electron moving from n equals 1 to n equals 3, so the atom's got to be taking in energy. So right now, before we even start anything with calculating this problem, we know that the change in energy should be positive for this particular answer to this problem. And you might say, how is it that we know that? Well, we defined a system that is taking in energy from its surroundings. That, when it's taking that in, we said the change in energy for that system would be positive. We said if that system, that atom, is giving off energy, the sign of the change in energy for that atom would be negative. And so we're moving that electron further away. It's taking in energy from the surroundings in order to move that electron further away from the nucleus. So the change in energy for this particular transition should be positive whenever we get done. So that's going to be one way we're going to use to check that. So two different expressions we're going to use in a constant. The first is going to be an expression for calculating the energy at an energy level. We said that is minus the Rydberg constant times 1 over whatever the energy level is. So if it's n equals 1, it would be 1 over 1 squared. If it were n equals 3, it would be 1 over 3 squared. That allows us to calculate the energy of an electron at any energy level. Now, this particular equation works for the hydrogen atom. It doesn't work for other atoms, although there are adjustments that we can make to the equation to make it applicable to other atoms. It was derived for hydrogen because hydrogen has 1 proton and 1 electron, so it's it is the simplest atom on the periodic table, the easiest to study, and so it was the first one in a lot of ways that a lot of this could be solved for. So hydrogen, very highly studied because it's that simplistic system. Our change in energy, remember we said change is always final minus initial. So in this case, it's going to be the energy at the final state minus the energy at the initial. And we said initially that's n equals 1, and finally that's n equals 3. So the energy at n equals 3 minus the energy of the electron at n equals 1 will tell us what that change in energy will be. And lastly is that Rydberg constant that goes into this equation, which is 2.179 times 10 to the minus 18 joules. So let's get started. The change in energy for n equals 1 to n equals 3 is going to be equal to the energy at n equals 3, the final state, minus the initial state, the energy at n equals 1. Okay? Now we can start to plug in this expression for energy. We're going to leave the Rydberg out for a second. And that change in energy is going to be minus the Rydberg constant. I'm going to put this in brackets, times 1 over 3 squared. And from that, we're going to subtract the energy at n equals 1. So minus the Rydberg constant times 1 over 1 squared. So we've got our expression. Now we're just going to type, or go and insert the We're going to insert the Rydberg constant in, solve, do those square terms, and then it's all going to be just math and simplification, some multiplication, division, addition, subtraction. So I'll set it up and let you solve it on your own and give you the answer. So minus 2.179 times 10 to the minus 18 times 1 over 9. We're going to subtract minus 2.179 times 10 to the minus 18 times 1 over 1, or 1. So we've got our expressions. Divide this Rydberg constant by 9, this Rydberg constant multiply by 1, or in other words, you don't have to do anything to it. Subtract those two terms, and your change in energy should be equal to 1.937 times 10 to the minus 18 joules. Remember, we said at the very beginning of the problem when we were thinking about changes in energy, and we said, okay, if we are taking in energy from the surroundings, our change in energy is positive, and indeed in this case, that change in energy is positive. So in that sense, this answer makes, there's some logic to it. It fits what we know about energy changes. So it makes sense. One other thing that we're going to find, because we're going to take this in the second problem, and we are going to figure out what photon, what wavelength of photon would correspond to that energy. So we're going to sort of go back to that light physics type work that we were doing previously, and figuring out what wavelength of a photon that would correspond to. And it's going to fall within the ultraviolet range, somewhere around the visible, and somewhere in the hundreds of nanometers. And so in that sense, the answer is going to have some physical significance to it that makes sense to us as well. So here's how we calculate, using the Rydberg constant and the energy level, here's how we calculate changes in energy for electronic transitions between energy levels.